Hello everyone. Welcome to this seventh lecture of this series, Generative Deep Learning. Today we are going to code actually the encoder decoder thing and make a generative model that will generate the images from the MNIST dataset. It is fashion dataset. So we are going to generate images here. It will be something in the preliminary phase, we will doing it, but in the further lectures, we'll be doing it in the real cases. Guys, if you haven't watched this previous lectures, please go and watch those lectures. What is the variational encoders are, so that you'll have a clarity that what is going to be. And in this video series, there is main goal is to learn that how a generative AI model actually works and how to make it from the scratch. Okay, using chat GPT is okay, but if you really want to be a elite learning engineer or want to build something interesting, then that needs the basics and the fundamentals of the chat GPT or any model, how to make models, generative AI models. Let's have a look that where you were. So we were at here auto encoders and denoising models. So what is denoising models? Denoise, if you are getting it, then denoise means to remove the noise. So what is the meaning of denoising? Why denoising is there? So let's have a example. We understand easily from the examples. The example is very cool. I hope you are like okay, you like or not, but this is Mona Lisa picture. You can just put your own blurred image also. So actually it take encoder take or it is auto encoders, it take the blurred image, and if you will train it now, if you'll train it on the denoise data, sorry, noise data, then it will be able to predict the clear output. So what is the real life implications of this thing? That is very simple thing. If your photo is blurry, then it can refine it, sharp it. Okay, there are furthermore implications of autoencoders, like if a section is cut here, then it can also regenerate that and match this thing, and it can also remove your background. So it is all dependent on the autoencoders, although it goes on the standard autoencoders like variational autoencoders that does these things very easily. So we will be seeing this thing, that what is this. So in the previous videos we have seen that there is an encoder part which takes the input. Just see this thing, there are three parts: one, two, three. One part is taking input, that is called encoder. What it will do is that it will encode the things. It will just encode, like there is a picture now. So it will just transform these pictures in the 2D vector. Okay. So how this thing happens, you can just have a look here. How encoder changes the picture into vector embeddings. So why I am googling it. It's just because that I want you to search about this thing. Okay. If you'll search, then you'll be getting that what is actually going on. Okay. So I will just tell you that just see this thing. If this is a picture, then it is actually coded into picture is actually matrix. It is nothing more than a matrix. So I'm showing you just 1 minute. I'm just finding it. Picture peek in the matrix number format. Let's see. Oh no, matricage pixels. Yeah. So I have taken this example also. You can just open the image in the new tab. So this is a Abraham Lincoln picture, and it is actually coded. Okay, how it is coded? It is actually that we have assigned white and black extremes 0 to 225, and that for the gradient it assigns a value, okay, to value to each the pixels. What is the pixel is the smallest size. So we have discussed this thing earlier. So actually this is the vector representation, yeah, that is the vector. Okay, so just see this thing. This is the complex image, okay, but here is the very simple numbers. I know actually why I'm saying numbers too simple. For the human it is easy to see the picture, but numbers are very easy for the computer itself. Okay, so if you are feeding it to the computer, we have to make it easy for understanding to them, okay, to the computers. So now just see this thing. So in the latent space representation, it does something, uh, and after that, decoder decodes the output. So I hope that you have understand the autoencoders part. Now just have a look here. It is a more clear representation, I will say, because just see this thing. Here is encoder part. We have given a input image like something like 2. So is it X is the input, and here it is hidden. That is the latent distribution. Okay, and then decoder is there for the generation of images. So it generates the image. Okay, so you will be thinking that these both images are same, but I will tell you that yeah, this is reconstructed image, because in this smaller thing you are not able to see this thing as a different thing, but yeah, in the coding part we'll be seeing that how it is getting different stepwise. Okay, so let's have a look here. So we are going to learn about encoder. So we'll be coding it. Okay, so first thing that we are coding it. So the codes are here in the GitHub repo. So link in the description. Just go there, just open this thing and just click on the open in Colab. Okay. So here you will be opening it in Colab. So I have already opened it in the Colab. So I will just exit it from here. And you also. So I'm just splitting the screen, guys. So okay, I am just making it a small. I hope that okay. So first, what is encoder? Encoder is something that takes the input image, map into the embedding vector. Okay, so it changes in the vector. That is the very simple thing, not a big issue. Okay, now, so what is how it is made? So we are just going to run one by one. So we are preparing the data here. I hope you are looking. You'll be identifying it more when you'll do it hands-on coding by yourself. Uh, because because computer screen is limited, of course. Okay, I'm just making it more. So we are just pre-processing the data. Okay. So we are running it, then this and this. So there, that was the data processing part. We will be just not going into that. We are going to build encoder. So what is encoder? So you will be seeing this thing that there is an input layer. So just see here, there is an input layer in the code. I hope you are seeing this thing, input layer. Then there is a convolutional 2D layer. Here is convolutional 2D layer. Then there are three convolutional. So one, two, three. So there are three convolutional 2D layer. Then then what will do? It will flatten. Okay, it will flatten up the shape. Okay, so why we are flattening it? So actually, decoder will use it in the further cell. Okay, then the okay. So here is the flatten. Okay, so you can see here is the flatten, and after that there is a dense layer, and then we can just run it. So this is going to be the decoder. So sorry, encoder. So encoder is that input layer is there, convolutional layer is there. So what a convolutional layer does? So just have a Google search. What a con convolution convolution layer does? You'll be getting the answer. It actually they extract the features. It extract the features, narrow it down. You just see this thing. Open image in a tab. So our videos are somewhat longer because of course, just see this thing. Here's the image. So what convolution does? Convolution is just extracting some features. Then here is convolution also. Pooling layer is also there. So it actually extract the features from the images. So they see the different features. What are the features? If I am talking about features, then what is the features? Features are basically for this image, just see this. So eyes are the features, nose are the features, curved line, dark line is the features. Like here is curve, so this is the feature. Here is the slant line, that is the feature. Here is the horizontal line, that is the feature. So actually CNN, sorry, convolutional layer actually extract the features. So um, now let's go to the this is the coding part. So stack convolutional layer significantly top on each other, okay, and then flatten the layer to a vector. So why we are flattening? So actually we have this matrix, so we are flattening it to a vector, okay, to a 2D vector especially, and connect this vector to the 2D embedding with a dense layer. So we are just connecting it to the 2D embedding. Fine. So now let's go forward and we'll be writing the code for. Actually, I am not writing, but when I do the tutorials, like I learn from it, then I also write. So you should also write this thing because you'll be getting more practice of this thing. Fine. So what we are doing, we are going to reshape it. So here is the shaping, and then we are going to do a convolutional 2D transpose. What is the transpose? It is almost the, you can say, no, that is opposite, the opposite of convolutional layer. You can just see this. Instead of the convolutional layer, we use convolutional transpose layers. So what is this thing? So actually convolutional layer half the size of input tensor. It actually half the size. I have said, it extract the features. Means there is a picture, then it extract the feature that there is a nose and there is eyes. So it extracted that if nose and eyes are matched, then this will be the person, something like that. So that is just for example. So what a convolutional transpose layer does, that it doubles the size of the input tensor. Okay, so it is something opposite to the convolutional layers. Okay, so here are three layers, and then you can see here that there will be a convolutional 2D layer. Okay, so now at the end there will be convolutional 2D layer, and after that we are just doing it now. So we just run it. You can see here the decoder output is there, convolutional transpose were there. So this was the whole thing about the decoder part. I know that this was the encoder and decoder, but what about how to combine them? To combine them, there is very good thing is that Keras library have very good features to connect them. You can see the code here. So there is a autoencoder is equal to model.model encoder input. What was the encoder input? The model we made. This is the model we made. So encoder input, we have written down the layers. So guys, we are making a generative model now. So encoder output is here, and then decoder 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 input is here. Okay, so just see this thing. Encoder input, we are just putting it encoder input, and in the decoder we are just inputting the encoder output. So what we are doing actually, that in the decoder we are putting the encoder. Okay, so we are in the decoder, we are actually this is the decoder, we are just putting the output of the encoder. So that is the sim. I hope you got it. Okay, encoder output we are putting in the decoder. So we'll be just running it and it will give a autoencoder summary. It gives the summary of the layers. Fine. So we'll be training it now. So we have now connected the encoder and decoder together, something like this, something like this. Now we'll be training it. So we'll be training it in the ADAM optimizer and binary cross entropy. So now you can just have a look that why we are taking the binary cross entropy. So for the overview, I will say that this is the effect that slightly this has the effect of binary cross entropy loss producing slightly blurrier image than RMSE loss. So but there is a one technical parameter that but sometimes this is desirable as RMSE can lead to the obviously pixelized edges. So it actually generates the edges. So that's why I think we are taking the binary cross entropy. So so fine, like this is going to be your task that why we are using binary cross entropy. And in the next video, I'll be discussing why we have used this thing. Okay. So now, now what we are doing, we are just we are making a model checkpoint to save it, and then we are training it. So here you can just see. Okay, we haven't compiled this. Compile it, compile it, and compile it. So we are fitting the X train. What is X train? X train was actually here you can see we have imported this data. So what is this data? This is the MNIST fashion data. Okay. So wait a minute. So we are just removing this thing. I hope this is now clear for you. So here we have downloaded the data in the X train, Y train, X test, Y test. Now we are inputting it in the model. Just see this thing. Train the encoder. So this is actually training, and guys, it is going to take some time, and after that we'll be saving it. Okay, so here in the files it will get saved. Okay, so we are going to reconstruct using the autoencoder. We are going to reconstruct the images and we'll be seeing this thing. Okay, now let's have some theory about it. So now we have actually we are training now the model which has the encoder and decoder. So I hope that thing is clear to you that what is the encoder and what is the decoder, how to write the codes for that. Now we are going to reconstruct the images. Like you can see this that we can test the ability to reconstruct the image by passing images from the test set through the autoencoder and comparing to the original image. So just see this thing that this is encoding, this is decoding. I hope it is clear to you. So this is decoding, this is encoding. So it is a slightly blurry image. You can see. So now notice how reconstruction is not perfect. So there are still some details that original images are not captured, such as logos or something like that. Just see this. This logo is not captured now. So how the encoder is represent? So we are going to investigate. Like we are going to see that how what is happening in the latent space. So here is the latent space. I hope you here are three parts. We have talked about encoder, we have talked about decoder, but what is happening in the latent space? So this video is of course going large, but we are discussing a very important thing that what is going to be in it. So we are going to visualize by this code. You have to just copy paste the code. Like you can see also that we are going to predict the example image, and we are going to see this thing plot of latent space colored in clothing table. Okay, so you can see, have a look on it that 0, 1, 2. What is 0, 1, 2? So actually this is the t-shirt, trouser, pullover, dress. That is the 0, 1, 2. So you can just have a look on it. So we can color each point, and even though the clothing's never shown. Okay. So what it is showing actually? So each black point represents an image that is embedded. Okay. So actually it is showing that how in order to better understand how it's structured, you can make use of labels. Okay, fine. So it is showing that how picture is embedded um, in the latent space. Now we will be going to generate the new images, that how to generate new image after getting trained. I hope it is training. Okay, so it is going to be some significant amount of time, but as the model output is already there, so I'm just going to show you something. Okay, so this was the black images. Now you can see it in the colorful manner, that what is going to be there. So actually, nine, you can see zero is t-shirt. I think you can just compare from here. T-shirt, okay, zero is t-shirt, and nine is ankle boot. So it is actually drawing um, on this map. Okay, yeah, on a graph. So generate using the decoder. So we'll be generating it, but you can see just here. Here is the points you can see, and it is generating the images now. Just see how it is generating. So let's have some theory about it. That what is saying. So we can generate noble images by adding some points in the latent space. What is saying? That we can generate a new image by just adding some points in the latent space. Okay. So, and using the decoder to convert back into the pixels. So you can just have a look here. This is the example that we have added some points here, blue dots. One of the images shown in the diagram where they notice how some generated rhymes are more realistic than others. So it is getting better, I think. And now that there are few observation overall the latent spaces, that some clothing items are represented very small area and very much larger area. Okay, so why it is happening? So this is actually there is a question about it, that why there are some materials you can see that pant is here, that is more realistic. So is there more realistic? You can't see this thing what it is. Maybe this is a bag, this is a shoe, but why some generated items are more realistic than others? Why is this? So there are some several reasons. We are going to discuss this thing, that some clothing items are represented over a very small area, okay, in the latent space. Now distribution is not symmetrical. This is also a point, and large gaps between the colors containing few points. So these three are the main regions. Okay, so you can just have a look here again. And now a part of the latent space carved out of the bags is larger than the ankle boot area. So there are some areas that are more, like red is more, of course. The red is more here. You can see uh, blue is here in the significant amount, but you can't see the yellow part more. Green part is also less. You can see. So so this is actually a non-uniform thing. Okay. So what is why it is the problem? So you can see that we can see the holes in the latent space. There are holes in the latent space that where none of the original images are encoded. Matlab, there are some points where the original images are not encoded. So what is the problem with autoencoder? Just see this thing, that a space is continuous, that it is not forced that a space should be the continuous. So that's what a variational autoencoder solves the point. So why this happen actually? That why it is not uniform? So the autoencoder only has a small number of dimensions to work with it. Okay, it is just slide down into 2D vector. That's why it squares the clothing groups together, resulting in a space between the clothing very small. That's why. And however, we start to use more dimension in the latency space to generate more complex images. So adding more dimensions to this autoencoder, you can generate the complex images like faces. But the problem is there itself. So we have to convert our model into variational autoencoder to solve this issue. So it is actually bottlenecking the thing. So we'll be seeing this thing, variational autoencoders will be again making it more understandable that what is going to happen. Although this, I know that this thing is going somewhat lengthier and technical more, but we will be seeing it in a somewhat easy way. Of course, this is somewhat high level mathematics is also there. Some complex concepts are there, but I hope that you are getting somewhat. Maybe you are getting 30%, 40%, 50%, and do some your own research also. Uh, and we'll be meeting in the next video. I hope this you like this video. So if you really like this video and if you get some value addition in your life, then please like this video and subscribe my channel. Thank you so much.